The animation you're looking at right now is the culmination of a year of research trying to characterise the mechanical properties of a bullwhip imparted to it by its maker. In this video, I'm going to explain how we got to this point and what it means, but first let me explain where this project came from. Whips have been around for millennia, and in that time the craft of whip making has been constantly evolving. As new materials become available, new techniques have been developed to work with them. A whip handler might try several different whips before they find one that's just right for their purpose, and each of those whips is the result of a labour-intensive, iterative design process. Even today, when the means and information to learn whip making are more widely available than ever, repeatability of performance from whip to whip is only made possible by the years of experience that professional whip makers have accrued. If there were a way to make a whip capable of mimicking the performance of a handmade whip, whose mass and stiffness could be tuned at each point along its length, to alter how a wave or loop travels along it, this could really speed up the process of finding the right whip construction for a specific task. For example, we could take a series of rigid sections and join them end to end with joints whose stiffness we could try and match to a real whip. But in order to even think about designing something like that, we need to know the stiffness at each point along the whip, what affects it, and how that relates to the dynamic behaviour of the whip. That's where this project comes in. Our research questions are: 1. What form does the restoring force in the thong of the whip take when it's bent? 2. How does this affect the whip's movement? 3. What tests can we do to relate the stiffness of the whip to its real-world use? And 4. Is the segmented whip we talked about possible? To conceptualise the whip, we need a theoretical model, one we can construct with data that can be gathered from a real whip without damaging it. For that, we've chosen a lumped parameter model composed of masses joined by linear springs, which is valid when the displacement of the whip is only small, and is often used to model beams, which is what the whip was modelled as in previous research. For this, we need the mass and stiffness at each point along the whip. To measure the mass, I weighed the whip and found its centre of mass, in order to estimate the mass of the thong, and then I assumed that the mass for a given length of the thong was proportional to its volume, since it's impossible to directly measure the mass of each section without cutting the whip into pieces. The stiffness was measured using a 3-point bend test. Starting with a stand, a 100mm section of the whip gets clamped in place to isolate it from the rest of the whip. Then a set of pulleys can be attached to the centre of that section, along with a dial gauge to measure how much it displaces when a mass is hung from the end of the pulley cord. This was done at 50mm intervals along the whip with a range of different masses, and here's what that resulted in. The dots show individual data points, and the lines are the lines of best fit for each section of the whip. We can see that the stiffness increases as the whip bends more, and by differentiating these displacement functions, we can find the stiffness function for each section of the whip. This tells us two important things. First, we can see that the stiffness of the whip depends on how much it bends, and secondly, we can see that as you get further from the handle, that dependence on displacement decreases until halfway along the whip, where the stiffness is almost constant. That answers our first question. Now, coding our lumped parameter model in MATLAB, the estimated stiffness functions for each section of the whip can be used as the springs in the model. Disturbing the first mass in the chain results in a wave moving along the whip and increasing in amplitude until it reaches the end. Let's compare that to a model where the stiffness doesn't depend on displacement and just varies linearly along the length of the whip. There's definitely a difference, but the most obvious change is in the speed the masses are travelling. Here's the model we just saw, where the stiffnesses are constant values. And here's the model based on the whip. What we see is at the point where the smallest mass reaches its maximum speed, in the constant stiffness model, the kinetic energy is distributed between several of the masses in the system. Whereas in the whip-based model, the speed of all the other masses is much closer to zero, meaning the whip-based model does a better job of concentrating the energy at its tip. The force input for these models was a little different. Adjusting the magnitude of the input force so that the initial wave was the same size, the whip model required a force 4 times as large as the constant stiffness model, but reached a maximum speed 5 times that of the constant stiffness model. In real terms, that means if you were to handle a whip based on the constant stiffness model, and a whip based on the measurements taken from this whip, the latter would probably feel heavier because it offers more resistance initially, but it produces a greater response, so the overall feeling might be that it's more responsive than its counterpart. We now know that the specific stiffness that the construction of a whip produces has an impact on how the whip moves, answering question 2. To answer question 3, the next step would be to test this directly by doing what was done in the simulation on the whip itself. This would involve hanging the whip up and introducing a vibration at one end, then measuring the movement of different points along the whip with a laser vibrometer to compare the computer simulation to reality. That brings into play other questions like what's the effective loading rate, friction and damping, but that's outside the scope of this project. As for the question of whether making a segmented whip is possible, maybe. What we can say for sure is we have an idea of what form the stiffness of a whip takes, and we know a segmented structure can produce a whip-like effect. So the concept is worth exploring. The challenge would be finding a mechanical linkage whose spring function could be fitted to the spring functions of the whip. That's it for this project. I hope you found that interesting. Thank you for watching.